Hello and welcome to PMCD MATHS Teaching. This session we're looking at real life graphs, and this will lead into distance time graphs, velocity time graphs and acceleration time graphs as well. So without further ado, let's get started. We'll look at the rationale for this. As usual, you can pause to read this. Let me smooth that out of the way. Pause to read this in full, and when you're ready, we can move on. Okay, the sequence for teaching. So they do need to be able to find the gradient of a straight line, and I've done a video on gradient if you want to look at that. And before moving on to the real life and distance time graphs, because we're going to use the gradient to find velocity and acceleration at some point. Obviously, this preempts work on non-linear graphs, non-linear travel graphs with velocity, acceleration, finding velocity and acceleration using tangents from either velocity time graphs or distance time graphs or displacement time graphs, if we're going to be more precise. Okay, so where do I start with this one then? Well, really, we'll start of these lessons, because real life graph, I use whiteboards for this one as well, and it's a bit of time to think here. I find this a really nice activity. I think they've got this resource from 10ticks, which can be used, and I'll display this and then ask students, to match the graphs to the glasses, and then I'll follow this up with perhaps one that isn't matched, and ask them to draw a glass for another graph. I'll draw a graph and then ask them to draw what the glass would look like. Okay, so there's only 4 graphs there. So there's only 4 glasses, and then what we can do is the graphs for the other glasses. So, and you can get a good assessment by doing this of what students know and how they're actually seeing this. So what sort of things are we looking for here? Is the depth increasing at a constant rate? Which one of these graphs shows that? So there's a lot of questions you can get out of this, and this is going to help with the distance time graphs a little bit later on. This one, number 2, and number 4 is increasing at 2 constant rates. So what does that imply about the glass shape? What's happening with this one here? This depth of water and time here. What's happening here? Well, you can see the rate at which the depth is increasing as well. So it's filling up faster. The depth is getting faster and faster. When would that happen? Okay, so there's lots of discussion here, and to understand how to analyze a graph like this. As time increases, what's happening to the depth? And I think if you keep using that word, that sort of expression, as time increases, what happens to the depth? They get the idea of how to start to build up a relationship between those 2 quantities and be able to give sentences. And I said verbalization is very important here. If they just say it gets bigger, it gets faster, try and get students to give their answers in full sentences when they're explaining this one here. What's happening with this one? Okay, what happens? It starts off, the depth increases slowly, then it's more quickly to this point, and almost stops and does again. Same sort of thing. So those 2 shapes there imply that the glass has the same shape between there. So we look at the glass, which one's got the same shape? The only one I can see up there at the moment is D. So let's see if that makes sense. Yes, because it's narrowing, the depth is going to increase very, very quickly as it gets to this point here. It's going to flatten out again and do the same again. So it really gives them a feel of how to analyze these graphs. So this is very useful a little bit later on, as I said, with distance time graphs. You can then, things I've done before is get them to write stories then. What's happening? What's happening here now? Again, as time increases. So what I would do is say between A and B, what's happening? I might even write on the side here. I want you to write a sentence for what's happening from A to B. Okay, so A to B, and then you give me a sentence. B to C. You write me a sentence. I want a sentence that you can read and make sense, not just it gets bigger, it gets smaller. That isn't good enough. Some other examples here are swimming pool one. Okay. Hot August, and there's lots of implications there. So these are nice little activities because they can really visualize and relate these graphs to what's happening in real life. And there's an old SATs question there as well. Okay, right. So what have I done here with this? Well, I I'm going to go back actually because that's going to start playing straight away. There's a video on the next page. So what I did is this is another one of the videos that I made. Probably 2011, I think I made this video, and again to help students anchor their understanding of something real life, a real life event. I went out and did a little run. I got my wife to film me, and then with a bit of simple video editing software, I just overlaid some information on that video. Now, just a warning: this video it doesn't play as large as on this as I would have it. I'd have it full screen. But what then I do is I gave the students, I gave them this printout. So I've got a graph, and I've got some information down here, a table. So what I asked them to do is, as they're going on, you have to be very observant. Don't, once you've got over your laughter of me in my running gear, okay, you have to write down the information that comes up on the screen, because that's going to enable you to draw the travel graph. Okay, so we'll quickly show this. And what I've done here, and this is something you could do in your own area around your own school, but I found somewhere where that was local and local to the school, somewhere students may have even gone themselves. So it is not disconnected from their life that they live in or the area that they live in. And the idea of that is hopefully to make it more interesting for them. And maybe, I encourage them to go and visit. I mean, I'd encourage you to go and visit this beautiful place. But okay, so you see, here's the video. Information's here about where it is. And this was the run. This second map is the run, and it shows where it's from, the monument to Ashridge House. And let's... Okay, you join me at Ashridge College. We're going to start our journey just here on this line, and we're going to run right to the monument and back. And we're off. That was the first bit of information. A million miles away, a message to the main. Oh, the seasons come and go, but I will never change, and I'm on my way. Let's go. Yeah, you're listening now. They say they ain't heard nothing like this in a while. That's why they play my song on so many different dials. Cause I got more hits than a disciplined child. So when they see me, everybody barracks. Man, I'm like a young gun, fully black barack. I cry teardrops over the massive attack. I only make hits like I work with a racket and back. Look at my jacket and hat, so down berserk, so down to earth. I'm bringing gravity back, adopted by the major. I want my family back. People work hard just to get all their salary tax. Look, I'm just a writer from the ghetto like Mallory Black. Man, where the hell for the sanity at? Damn, I used to be the kid that no one cared about. That's why you have to keep screaming till they hear you out. Written stars, a million miles away, a message to the main. Oh, the seasons come and go, but I will never change, and I'm on my way. Okay, so you get the idea. Anyway, again, I'd encourage, it's a brilliant place to take your family, Ashridge, and quite near to Berkhamsted or Hemel Hempstead. You can find it on the map. But anyway, you can do this in your own area. Wherever you live, you could make this video. And the great thing about it is once you've done it once, it's there for year after year, and you can apply it in different ways. And honestly, the kids love it. They love looking at me when I was younger as well, so they like to have a laugh at that. But like I said, you need to be able to laugh at yourself, and just endears you to the students and builds those relationships with them as well. So once they've filled this information, ask them to draw the travel graph, and it's distance and time, and this is in minutes. So we've got meters per minute when it comes a little bit later on, which is not an SI unit, but for the purpose of what we're doing here, it's good. So the graph they should end up with, if I just make that a little bit larger, is something like this. Okay, and again, you know, we talk about what's happening. They describe what's happening here, and we start talking about, okay, you know, how far did I travel altogether? You know, how fast was I traveling at each stage? Okay, so this is where the gradient's going to start to come in here, and that's why they've had to do the gradient before this. So what I would do again is say that O to A, what's happening? Okay, you can, and I'm asking for sentences here. So I'll say O to A, he ran 300 meters in 2 minutes. Okay, so this means his speed was, and you can give that that value there, and obviously they can be encouraged to use the triangle method if you want, or you know, whatever method you prefer. But I mean, the triangle method is going to work nicely here. So the vertical distance being 3 minutes, in about 300 meters in 2 minutes. So my speed is equal to distance divided by time. You can, and this, if you haven't even taught this formula at this stage, you know, you can get the idea that how do we change our velocity? It's how quickly we change our distance. So we change 300 meters in 2 minutes, which gives us 150 meters per minute. And they, you know, they can write these calculations on their sheet as well, for something they could stick into their book here. Okay. So there's a bit of discussion there about speed. It's a good idea to actually, if you have not done this yet in a speed, distance, time sort of lesson, then what you could do is you can talk about this. Well, when am I traveling fastest? I mean, intuitionally, a lot of them will understand that you're traveling fast between O and A than you are from A to B on this particular run. They say, well, why is that? And the whole thing about steepness sort of comes out of that. Okay, why? Really push for that. Okay, well, between O and A, you've run 300 meters in 2 minutes, but between A and B, I've run 300 meters in 3 minutes. So obviously, it must be going faster. What? So the steepness comes into that. How can we actually work out what that means? And then come back to that gradient. Well, look, you can see what you're actually doing to get this value. Is saying, well, that means I'm doing 150 meters per minute from O to A. That's that vertical divided by the horizontal, which fits into what you were talking about gradient. So it's great to mesh in and jigsaw those ideas and those concepts that you've taught before, and rather than teach them as separate things, try and bring that in at every stage you possibly can. Okay, and then, you know, there's lots of stuff. You can make a whole worksheet of this as well. So things I talk about, well, why is it taking me fast? Why is it taking me longer to get back? So if you look at it, how does it take me to get back? It took me 8 minutes to get back from the monument. It took me 7 minutes to get there. Why is that? Okay, so more tired. What about this velocity here? Okay, what's happening here between D and E? Why is it coming down? You know, that speed there. So they say, well, okay, you can work out the speed by the gradient, but that gradient again is negative. So what does that mean, a negative speed? Well, we can't have a negative speed, so you can start bringing in velocity. Okay, velocity. We can have a negative velocity. That means we've got a speed, but it's now in the opposite direction. What's happening between C and D? Okay. Now, the other thing to mention here about misconceptions is if you'd shown this, and I think when we go this sort of graph at the very, very start of your lesson, so if I look at this one here, you might show something like this and say, what's going on here? This is a distance time graph, what's happening? You will get students who think that means you've gone up a hill, got to the top, and come back down again. Okay, because it's got to a height of 700 meters and then cut back down again. Okay, so, and that could be true. That could be true, but it's not necessarily true. So these graphs are not all about people climbing up and down hills. So yeah, so going back to this graph, lots of things you can ask about this. Okay, and I get them to O to A to B, B to C. Again, A and B and B and C have the same speed because they've got the same gradient. It's a nice way to show it's on the same line. It doesn't matter whereabouts on a straight line you find the gradient. what 2 points you use, you'll always get the same result. Okay, so you can make your own up from that. Now you can use this, or you can make your own. And I think the more personal you make it to yourself, the more you're going to enjoy it, rather than using somebody else's version. It isn't that hard to do, especially with software that's out there for phones and laptops now. Once you get the hang of this, it's a really useful skill, actually. And as I said, students love it, and it's always good to have a laugh in a lesson, I think. Okay, so what do I follow this up with? These are from resources that I picked up over the years. This was something called the standards units. And if you search for that, you probably find they're on TES. But they were fantastic results in here. And this one was all about writing, and now they've shown that understanding of travel graphs. So if you look at this one, they're actually having to write a story about what could happen. And the great thing about it is there's lots of variety of stories that could have happened here. Okay, so it could be what's happened here. Distance is travel from home. 50 seconds were walking at, and we can say what speed they were walking at. Then what happened? They started coming back towards home. Then they went faster and waited. Now, why did they have to go back towards home? Don't know. Maybe they saw their friend and walked backwards, right, and to join them, and then realised they're going to be late, so they ran. Or I've had people saying they dropped a purse, they dropped something, had to go back to look for it, found it, and then had to run for the bus. And this bit here is waiting. So it's a really good way to understand whether they've grasped what a travel graph is showing. And a second one of these here, some questions I've added up as well about a car and a motorbike. What's happening at that intersection? And this is important, I think, especially when you get to velocity time graphs, because velocity time graphs, the intersection, a lot of students will transfer their understanding of distance time graphs. Oh, that means they're at the same place. In this case, it is the same place. This is when the motorbike overtakes the car, isn't it? Because the distance from the start is the same. Okay, so some good little questions. You can add your own there, but the standards unit, I'll say that again, the standards units, I think they were called TS, you'll probably be able to find those. You should be able to find those if you search for those, and they were free. So moving up, this is a great foundation then if you are going on to velocity time graphs. We talk about the difference in velocity and speed. And again, I've got here, take the graph from the Bridgewater, it's the Bridgewater Monument. That's why I've called it that, because that tall column is what the monument's for the Earl of Bridgewater, who is supposed to be the father of inland navigation, just for the historical context there. And because there's the canal, they use the canal for transport of materials up and down the country. So, okay, so this one here, there's the graph. And then what I've done underneath it, I print this out, the whole thing, and give it to them. Because now what we're going to do is work out the velocities. Now, they've already done this. But what would the velocity time graph going to look like? Well, we said between 0 to 2 minutes, okay, the velocity was 150, wasn't it? So if we look at that, and we're talking about our unit's 150 meters per minute. So how does this appear on a velocity time graph? Well, down below, we draw that now. So for 0 to 2 minutes, we've got 150. So it stays at 150. And this is where you start getting into, is this realistic? Would I have been traveling at that constant velocity? Would it be slightly above or below? We expect it to be a horizontal line. 2 to 5 minutes. I think that was, what's that? That's 300 meters into it. That's 100 now, isn't it? So look what happens here. 2 to 5 minutes is 100. So what's happened? I've instantly changed to a slower speed, or velocity, I should say. A slower velocity. Is that realistic? I'm running along, boom, straight away I change. It doesn't sound realistic. So they can start getting the idea that these graphs are showing average velocities, really, and that if you want something more realistic, what's going to happen? We're going to get more curved shaped graphs. So you can carry on with that. Notice that between 12 to 18, you're going to get a negative. So graphs are a really nice way to show that, and it links to what they've already done. So we're building for something and using the same resource in more than one way. And some questions to follow. And then reverse, you can then do something where you actually having to find a velocity time graph from, using a velocity time graph to find a distance time graph. Okay, so leads into that nicely. So there's a velocity time graph. How do they find the distance time graph? They're reversing that, aren't they, of what they're doing here. So this is in meters per second, 20 seconds, 80 meters per second, so 20 meters. So they can use the formula, the distance, speed, time, in conjunction with making sense of it from the graph. If I'm going 80 meters per second for 20 seconds, that's 80 times 20, that's going to be 1,600 meters. 80 meters per second. Sorry, that's wrong, isn't it? If we're actually going from 0 to 80 here, from the previous part, what we should have identified from here is that the area under the graph gives us the distance. That would have been true. What I just said is the sort of error the student would make, isn't it? They'd say 80 times 20. Well, what is that? That would be the area of that would be the area, all this area here, this sort of rectangular area. And we know actually the area under graph is what we want. So we'd have to half that, so 800 meters there. And this is good practice at the start of introducing that sort of pre-calculus work on area under a graph is equal to the distance moved. And some other examples here as well. Okay, so another one here. Acceleration, then it leads into what is acceleration? You know, how do we get acceleration? I'll often refer to the car. You know, how do we actually change our speed in the car? The car is not often measured by how fast it can, you know, the acceleration of the car, especially performance cars. And it's how quickly a car can change its velocity. How do we change the velocity in a car? We put the accelerator down. So it sort of fits into what they know. What are the units used? Well, it's a change in velocity over time. So there we get a velocity is meters per second divided by time, which is seconds. So meters per second divided by seconds gives us meters per second squared. And you can, you know, I'm going to get bogged down into a units sort of thing here, really, but velocity, acceleration is going to be meters per second divided by seconds, which is meters per second times 1 over seconds, which is meters per second squared. And you know, if they've done negative indices, that's how we end up with this. It's amazing how many I get at A level who don't know where that's come from. And you know, to be honest, myself, I didn't. I just used to use these units without even thinking about it. But that's why it's ms to -2. It used to seem mystifying to me. Another run here. So we've got velocity for a different time graph, and what they're going to have to do is find the acceleration. So we're repeating this now, the same idea, the same process, but now we're using acceleration, getting accelerations from a velocity time graph. And some further examples there. Okay, so it's a launch pad for those sort of lessons. Okay, so I think I'll leave it there for now. I hope you've managed to get something interesting from that. I hope something, maybe just even if you get one little idea that you're going to expand and create from that, that'd be brilliant. I'd be really pleased to hear about what you do with that. Okay, so I will leave it there until next time. Thanks for watching, and I'll see you next time.